Okay, welcome back. Today we're going to be talking about function notation. This is our new topic. So, function notation, as I have it listed up here, is a new way of writing things that we actually pretty much already know. So, the first thing I want to say is we're going to look at y, as in like y equals mx plus b. And you should already know this is a line, and this line is a function, because we should have already watched the videos which talk about what a function is and what it is not. So this is a function. And anytime it's a function, you're going to have a function with an independent variable. In this case, our independent variable is listed as x, because we're graphing on x and y. So the independent variable is x, but that means y is a function of x. That's what it means to be dependent. So the y is dependent, x was independent, so that means y is a function of x. Well, instead of saying all this, we can write it like this, that we have a, excuse me, that's not what I meant to write. So we're going to have y is a function of x. Y is a function of x, and we're going to use f to represent function. And this f is going to be the name of the function. So f is the name of the function, and inside the parentheses is going to be the variable or variables used. Okay, so we have function f using variable x, and that would be up here. So we could rewrite this top equation as f of x is going to be mx plus b. So that's what this means, is that we have a name of a function. Most of the times we call it f standing for function, of course. And then variables, in a lot of cases, it's going to be x, simply because we're often using things to graph, and we graph on x and y. So if you're ever seeing like y equals, you can replace that y equals with f of x equals, as long as it is a function. So let's look at some examples over here. So here's an example of f of x. This one has a function, and its function is, this is named f, and it says take any number, and then we're going to add 3 to it. So if I give you an x, you add 3 to it. So let's say, for instance, that I'd say that x is 1. You would say 1 plus 3 is 4. Well, we get to write that. So we're going to say f of 1. That's what this means. Go find function f, which is right here, and where that x is, you're going to replace it with a 1. So over here, we're going to replace it with the 1. So this x is now a 1. So it says f of 1 is equal to 1 plus 3, which is, of course, 4. But we could do this with any number we want. So instead of saying f of 1, let's say that we want to know what f of 4 is. So we go over to find function f, which is right here. We're going to replace x with 4, which replaces x over here with 4. So f of 4 is equal to 4 plus 3, which is 7. So f of 4 is equal to 7. And we could keep doing this forever. If you want to do f of 10, you'd have 10 plus 3, which is going to be 13. And it doesn't matter what you put in here. Wherever it is, you go find function f, plug it in. But we're not limited to just f. So in the exact same spot, we could also call for a different function. So this time I'm going to list g of 7. So what this says is go find function g. Well, this is not function g. This is function f. This one's function g. So we found function g, and then whatever we're going to do is we're going to take that 7 and we're going to put it where this a is. So that 7 goes there, and since it was an a, every a, including this one, is now a 7. So this function said 2 times some number a, so we know the number is now 7, so you're going to do 2 times 7, which is, of course, 14. If I said go find h of 7, that means go look at function h, which is here, and putting 7 in there. So that d is now a 7, so this would be 3 times 7 plus 1. 3 times 7 is 21, plus 1 is 22. So h of 7 was 22, whereas g of 7 was only 14. Now, one thing that I want you to caution, over here on the left-hand side, this does not mean, right here, h times d. That is not what that means. What it means is you have a function h that you are using variable d. Do not think of this as multiply. If you start thinking of this as multiply, you're going to start trying to solve for things and you're going to end up dividing. You cannot do that in any way, shape, or form. This is not a multiply problem. It is only a label. And the label says name of the function is h, and you're going to use variable d. That's all it means. So do not confuse that with multiply. So let's look at some of these other examples. When you get down here, there's no limit to how many things are in here. So I could say, go find me p of 1, 2, and that means go find function p. Here's function p. And use these variables. And the variables are important in the order. So it says what it was in the x spot is a 1. So these x's are 1s, and the y's are going to be 2. So it says go take all the x's. There's our x. Put a 1 in there. Go take all the y's. There's a y. Go put a 2 in there. And then do the operation. Well, the operation says add those together. So we'll do 1 plus 2 is 3. So p of 1, 2 is 3. We could also ask it for q. So let's go q of 1, 2. That says go find this one. And we're going to put in 1 and 2. So every a is going to be a 1. Every b is going to be a 2. So we got 2 times 1 plus 3 times 2. We would do this. 2 times 1 is 2. 3 times 2 is 6. And add them up, and you get 8. So q of 1, 2 is 8. And then just like before, you can do it anything you want. This one happens to say you multiply the two numbers. You could even have something like f of mn is equal to m plus n. You could have it more than once. That just means every single m. So let's say we had f of 2, 3. So every m would be a 2, so this is a 2, and this is a 2. So it doesn't matter that there's more than one. You just replace every instance of m with 2. And then, of course, the n in this case is 3. So it would be 2 plus 2 plus 3, which is, of course, 4 plus 3 and 7. And it doesn't stop at 2. You can do as many as you want. So let's say if we wanted to find t of 1, 2, 3, it says go find function t. There it is. And you're going to use 1, 2, 3. So the x is 1. The y is 2. The z is 3. And we have numbers next to each other, so these means times. So we're going to go 1 times 2 times 3. 1 times 2 is 2. And 2 times 3 is 6. So this is 6. So that's what function notation looks like. So if you have any questions, make sure you ask. But let's look at some other instances of function notation. Here's one of the nice consequences of function notation, is when you graph things. Because when you graph things, we know what x is, and we know that f of x is the other thing that's on the y. So x was always down here. So this axis up here is called f of x. So if I tell you that x is, say, 3, so if I wanted to know f of 3, because x is 3, you go find 3, and you get to tell me what it is. Well, you go up here to 3, and you go here across, and it's at 3.5. So you can read off a graph what f of 3 is, because it says go find 3, and then go over to the answer. And you could also work this backwards. Let's do another example before I do that. Let's say you want to know f of 10. So you go find 10 on the x, because that's what was replaced was x. You go all the way up until you hit your graph, which is right here, and you go read what that point is. Well, that point is at 7. So what this is saying is that if I'm at 10 miles, which is what x is, at 10 miles, we have 7, and this is cost. This happens to be in pounds, but you could easily make this dollars. So at 10 miles, there's a cost of 7 pounds associated with this. So you can ask the question the other way. Let's say I want to know what f of x is, but I know that f of x is equal to 7. So in this case, because I don't know what x is, but I do know what f of x is, I would go find f of x is 7, which is right here, and then I go across until I find my point. Well, this point happens to be at 10. So because f of x is 7, then I know that x must have come from 10. So you can go both directions. So if you know x, you go up and across. And if you know f of x, you start there and you go across and then you go down to find x. So let's look at another example. In this case, you can ask another question. Let's say that we start here at 5, because remember our y-intercept is 5. So instead of y, we're going to call this f of x. And let's say that we want to know, let's say this is dollars, and this is, I don't know, cans of something. Okay, I want to know how many Well, that doesn't make sense because we're losing money. So how about instead of cans, let's go with this is years. Okay, so how about when, as in how many years, is the value equal to 0? Okay, when does our object have no more value? So I don't know, maybe this is a car and this is in thousands, so this is 5,000. I want to know how many years until the car has no value. Okay, so according to this, no value is occurring right here. So this car has no value at 7.5, 7.5 years. So there's nice things that you can ask for this by just reading the graph. So at 7.5 years, this car has no value. We could find out what its value is at, I don't know, say 5 years. So at 5 years, we go on up and we go across. And let's say this is at, I don't know, about 1.75. So remember, this was in thousands. So this is going to be 1.75 thousand or $1,750. So that's how you could do it. So if you're given years, you would go up and then go across. If you're given the cost, so let's say you know that the vehicle is currently worth, say, $3,000. If the vehicle is worth $3,000, how many years is it? Well, you would start at $3,000. This is 3,000. Go across, go down. Well, that occurs at 3 years. So your car is 3 years old because it's worth $3,000. Okay, so this can be very, very, very handy, and it has some real life application. So let's look at a real life application of this. And that would be this chart over here. As I get it up. Here we go. So this chart is talking about U.S. population by region up until 2000. So it's not as current as I would have liked, but it's illustrating a point, which is all we really need to get out of it. So here's what's going on. I want to know what the population was of the United States in 1950. So I can go all the way up, and then I go across, and it was 150, and this was in millions of people. So this is 150 million. So in 1950, this is 150 million people in the United States. So you can read any chart you want. It doesn't have to be just a straight line, and that's how you can use it. So you can go up and across. You can also go across, and you can say, in which years did each region reach 50 million people? Well, the United States as a whole reached 50 million people in 1880, but none of the regions, which is what these colors are, reached 50 people until the 1950s, maybe about 53 or so for the red, which is the South. The green, which is the Midwest, reached the reached 50 million people in the late 1950s, maybe about 58 or 59. And it wasn't until all the way over here that yellow, which is the West, reached 50 million people, and shortly thereafter, in about the same amount of time, the Northeast also reached 50 million people, and that was in the 1980s, so maybe about 1988 or so, 89, somewhere in there. So it's really handy to be able to use a graph like this and read it. So you should be able to read both directions. That if I'm giving you an x, you should be able to go up and then read me what the f of x is, or the y. But if I gave you the answer, the y, you should be able to go backwards and answer questions both directions. Okay? And then lastly, what we're going to have to do is we're going to do the same thing, but this time with a problem. If you've not watched the video on decoding problems like this from story problems, go watch that video because it does a nice job of explaining where all these came from. But we're going to go ahead and go with this one. So we're looking for keywords in here, just like we did before. We have 100 feet. It's descending at 20 feet per minute, but now it's asking some questions after we have this information. So we know the rate of change is going to be negative 20. We know that the y-intercept is going to be negative 100 because it's 100 feet below the surface, and this is negative because it's descending. The dependent is still going to be feet. The independent is going to be minutes. And our equation is going to be y equals negative 20x minus 100. So here's how we're going to change it. So instead of calling it y, we want function notation now. So we're going to say that this is f of x. And why I picked x? Because we're using x over here. Since we're graphing on x and y, it should be f of x. You can change the name if you don't want f, but the x needs to be here because the x is over here. So we got f of x is equal to negative 20x minus 100. Now at this point, we want to answer these questions. You got two choices. Okay, so you have two choices. You could do either one. Choice one is graph. You learned how to graph last time. And once you graph it, then you could go back like we did over here, and you can just go across and up and down. So if you're happy with that, and these are nice data points, and you made a nice, beautiful graph so you get accurate answers, by all means, you can do that. Most of the time, however, we don't get nice data points, and most of the time, we don't want to spend all the time graphing, so there's some other things you can do. So in this first question, it says after 10 minutes. Well, minutes was our independent, which is x. So if I know x, then we can do what we were doing over here, which is just plug in things. So I'm basically asking you what it is, the x value here. So I'm asking you for f of whatever that number was. So in this case, it was f of 10. So the question is, what is f of 10? That's what after 10 minutes means. So instead of graphing this, we can simply plug in 10. Well, it says f of 10 is equal to negative 20. This x is now a 10 minus 100. Okay? Doing the arithmetic, you're going to get negative 20 times 10 is negative 200. Minus 100 is negative 300. Okay? So this is saying that after 10 minutes, you are 300 feet below the surface. Okay? And it's really important that you answer the whole question. Don't just say negative 300, but you are 300 feet below the surface. Okay? Because the question was asking how deep is the submarine. Make sure you answer the question. So the answer is 300 feet below the surface. The other thing you can do is, let's say you ask the reverse question. When will a submarine reach 400 feet below the surface? So again, you can go back and use the graph just like we did here, and you would start on the left side at 400, go across and go down and figure out what that x value was. Or what the question is asking is, if f of x is equal to 400, what is x? We want to go the reverse way. So in this case, I'm still using this equation, f of x is equal to negative 20x minus 100. But in this case, it's not x that I know. It's actually this whole f of x I know. So we're going to replace this whole f of x with 400. And I can do that because I know what f of x is. It was given to me. F of x is 400. Well, this is just a two-step equation. You know how to solve these two. So let's go ahead and solve it. You're going to first add 100 to both sides. So you end up with 500 is equal to negative 20. And then you're going to divide both sides by negative 20. So x is going to be negative because there's two negatives. And then 500 divided by 20, you can take off one of the zeros. 50 divided by 2 is going to be 25. So it says it's going to be negative 25 seconds. And that's because this really shouldn't have been a 400, because we want to be 400 below the surface. So this really should have been a negative. And when you put that negative on there, that negative goes there. And then this really shouldn't have been 500, should it have been? So I'm glad I showed you this, because this is like one of the most common mistakes. So that negative was really important. And the reason I noticed it was because we're talking about negative seconds. Answer should never be negative 25 seconds. That doesn't make any sense. So we got negative 400. And when we add 100 to both sides, you get negative 300 is equal to negative 20x. We're going to divide both sides by negative 20. So you got negative 300 divided by negative 20. The double negatives go away. That makes much more sense because we're now positive. So you got 30 divided by 2 is 15. So it's going to be 15 is x. So it's in 15 seconds. Or minutes, excuse me. This was measured in minutes. So in 15 minutes, this submarine will be 400 feet below the surface. And that kind of makes sense because in 10 minutes, we were 300 feet below the surface. So in 15 minutes, we are 400 feet below the surface. So I hope that helps. Make sure you watch your negatives. Most common mistake is the negatives. But you can solve it either way. And if you don't like solving it with algebra, you can always go back to graphs. And it depends on what's easiest for you. It also depends on how accurate you make your graph. If you're going to use the graph method, it has to be accurate because you're really relying on these points. So make sure if you're going to do the graphing method that you are very, 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 very accurate on that graph. If you have questions, please make sure you ask.